Hi, I'm Tachiwan, and my team members Wano Hidayah. In this lab 7, active filter, we are required to design 3 types of active filter, which are first order low pass active filter, and the second one, first order high pass filter, and third is the second order low pass active filter. First, to design low pass filter, the circuit is constructed as below, as here, and we connect the oscilloscope across the Vout and at the AC voltage here. Then we use 15 volt of V input as referred in the Texas Instrument datasheet. As our voltage don't have VRMS value, so we change the 1 VRMS to 1.414 V peak. So now we're going to run it out by using 10 kHz of frequency. Let's see what happens. This is our curve, and the output for the op-amp is 2.101, and the input is 1.399, which is pretty similar to the 1.414 V peak. Then we are required to change the frequency from 1 kHz to 1 MHz. And all the results are recorded in the form of table here. This for first order low pass filter, and we get the Vout from the simulation is this one, and from the Vout we can calculate the AV and AV in decibel. After we get the AV in decibel, we can plot the curve using this AV value. In this curve, we have two curves. First is theoretical curve, and second one is simulation curve. The graph is the AV against frequency. Then we are required to design high pass active filter, first order high pass active filter, and the circuit is constructed as here. Same as low pass filter, we put oscilloscope and the AC voltage power here, and we also put the 15 volt of input. And now we change our capacitor and the resistor places, and the value also change. The capacitance become 100 nanofarad, and there is a feedback R1 here. So now I'm going to simulate it, run it out, and see what happened. So for 10 kHz of the higher pass filter, we get the waveform like this. From the channel A, we get 3.060, which are V output, and channel B, which are 1.406, which is 1.414 V peak. They are almost same the value. So we change the frequency from 10 Hz to 20 kHz. And all the results, the view out is recorded. And we recorded Vout is here. And by obtaining the Vout, we can get FV and FV in decibel. After we getting the FV decibel, we can plot the graph, which is FV against frequency. The difference between the high pass filter and low pass filter is the connection. The connection of low pass filter, the capacitor is connected parallel with the R1, while for the high pass filter, the capacitor C2 is connected parallel series with R2, and R1 is the only feedback connected here. While for the low pass, R2 is here and the R1 and R2 is parallel and become the feedback here. For the third design, which is second order low pass active filter, the circuit is constructed as shown as here. We use R1 equal to R2, which is 3 kilo ohm, and C1 is equal to C2, 0.01 microfarad. And now we're using 30 kHz of the frequency. And same as previous one, we use 1.414 V peak, and the oscilloscope is connected across the V out of the OM and at the voltage supply here. Two extra resistors is added here, which are RF and RS. Now we are going to run it out and see the waveform. The waveform is like this. For the frequency 30 kHz, the channel A, which is Vout, is 69.349 milliwatt, and for B channel, which are Vin, is 1.400 watt. Then we change the frequency from 100 to 30 kHz, and the results are recorded. The recorded Vout is here. After we getting the Vout, we can calculate the FV and FV in decibel. From the FV in decibel, we can plot a graph using FV and frequency. The graph FV against frequency is plotted. The roll-off rate for the first active filter is 20 dB. It means that the high pass filter, first order high pass filter and the first order low pass filter, the roll-off rate is 20. While for the second order low pass active filter, the roll-off rate is 40 dB decibel. After we plot the graph, we can find the critical frequency, which is cut-off frequency from the graph. I think that's all from me about the Lab 7 active filter. Thank you so much. Thank you for watching. Bye bye.